What's up, YouTubers? So today I'm going to be tackling something that I've covered in previous videos, but not, I guess, to any kind of extent. And that's going to be what I call your heat to metal ratio. And this really applies extensively to wire welding, so flux core, MIG, spray arc, all of those, dual shield, and it also applies heavily to TIG welding. And to really understand this, learning to TIG weld is really the best way, I guess. But because it applies to everything, and it even applies to stick welding as well, I thought I would do a video just on this topic and give actual hands-on examples to where you guys can have a better understanding of heat to metal ratio, as well as understanding what you have to do to improve your welds, if they're running cold, if they're running hot, all of that. So that's what we're going to be diving into today. Let's get started. So for all you aspiring welders, you're going to have to understand heat to metal ratio, and the better you understand it, the better welder you're going to become, because you can troubleshoot your own welds. So what I have in front of us now is essentially two little short beads I did in a previous video. Now, just on face value, if we look at these, we can see that this weld is wider than this weld. Might be a little bit hard for you to see. This is a little bit taller than this weld. When we look at the penetration out the back, there's more melt through on this one, and our heat affected zone tends to be a little bit bigger than this. All of these are signs that this weld was run with more heat in relation to the metal that we deposited. This had less heat for the amount of metal. Now, if I recall correctly, both of these were run at the same wire feed speed with flux core wire. However, I increased the voltage on this, which resulted in a flatter, wider profile. And that is your heat to metal ratio. Basically, what the heat to metal ratio is that for a given amount of weld metal, so your wire, your stick rod, your TIG filler wire, whatever it is, that you want to push in, so the size weld you want to produce, you need a certain amount of heat to either produce a decent weld like this, a hot weld like this, or a cold weld, which would be more humped up and narrower than this. And let me show you a little plate I made years ago, and this should explain a lot more of it. So I apologize for all the rust on here, and you don't really have to worry about all the writing on here. You can barely read it anyways. But I made this back when I was teaching people in my home shop how to stick weld. And I thought this would be very handy for hands-on, like, so people can actually physically see the differences. And then by keeping this on a table in my shop, that if someone made a weld, they can compare it to this and understand where they're at. But you know, I forgot that I had this and dug it up out of the scrap bin and thought, well, wow, this would actually kind of prove a lot of what I'm trying to teach you guys in this video. So what we'll start out as, we'll look at this right here. Okay, these welds, which were probably done with, I don't know, 6013, I'm not really sure. This is 7018, who cares? When we look at the weld width here, these were all run with the same rod, just at varying amperages. Now in stick welding, where you don't control voltage as a setting, your amperage is your heat. So with stick welding, by adjusting your heat input, aka amperage, will produce different width welds. This far too low, this still far too low amperage, this is approximately correct, this also correct, this is starting to get too hot, excessive spatter, all sorts of things. And if you look here, you can tell just by the heat affected zone how much bigger it gets with every weld, and in this guy, massive, massive heat input. So not only do your heat affected lines on clean material tell you a lot about your heat input, but the width of the weld. Now this is a great example because the travel speed on all of these was run roughly the same. So it's not like to produce a smaller weld, I really move, super fast forward, and then to produce this wider weld, I moved really slow. These especially in here were run all at the same. So by increasing heat input, flattened the bead and widened it. It also, to a certain extent, improved the penetration, but there are limits on that. But anyways, back to what I was saying. You can see with all of these rods, this is like 6011, I think the 6013, even 7018, you see the same effect. Increasing heat input for the given amount of metal that you're depositing will result in a flatter, more wetted out weld. Same thing with, got 7014, 7024. You can see very drastic difference between too low of amperage, too much, and approximate right amount of heat input. So what I'm getting at here is, given the weld size you want to deposit, so if you're welding 1/4 inch plates, you're going to need a bigger weld than if you're welding 1/8 inch plates. So when you determine the size of weld, you can control your metal to meet that size weld. So now with stick welding, you can weld, anything 1/8 inch, 3.2 millimeter, 1/4 inch over 6 millimeter thick steel. Stick welding tends to fall apart on thinner material like this, which is like 22 gauge or so. Very, very difficult to weld with stick because your heat to metal ratio is limited by your rod size. Now, talking about stick, you can go with super small 1/16 rods or bigger 1/8 inch and even bigger than 1/8. So you have that control, that's how you control the metal you deposit with stick, is by choosing the appropriate rod size for what size weld you're running. And then your heat is controlled by your amperage setting. Well, with wire feed, which you can see how much smaller than this is 035 flux core, how much smaller that wire is compared to this, I think this is 1/16 inch rod. Massively smaller. So wire feed, be it flux core or MIG, has a lot of advantages on very thin material, and you can always increase your wire feed high enough to weld thicker as well. So you have a far broader range with wire feed than you do with stick for what you can weld easily. And you're not switching out wire as much. Like with stick, if you want to weld 5 different thicknesses of metal, you may have to use 3 different rod, diameters to do it. MIG, you can use 1 wire and probably do it. Now with that said, this is 035 flux core, they make 030. Just like with MIG wire, they make 023, 030, 035, 045, I believe, and so on. Well, your heat to metal ratio with flux core wire, same thing with MIG, comes down to how much heat for a given wire speed you need to run. If you run too much wire for your given heat setting, you're just going to make a roped up weld. If you run too much heat, you're going to make a flat weld that sinks in and probably doesn't have enough reinforcement. And I'm going to show you hands-on with flux core what I'm talking about. All right, so I got 1/8 inch, 3.2 millimeter steel, 035 flux core, and I'm gonna make a weld, and we're gonna look at it, talk about it, and then we're gonna make an adjustment together so that you guys start to understand heat to metal ratio. Now the settings I have my welder at don't matter, and you'll see why in a second. So let's put down a weld. So let's take a look at this together. See how that's crowned up quite a bit? Penetration out the back, no real evidence. We have really good heat affected zone lines, which that tells us our heat input was very consistent, which translates to we were very consistent. However, it's a little bit roped up. Now the question is, if we wanted to get our weld to flatten out a little bit, what would be the smart way to do it? Well, with wire feed, be it MIG or flux core, we have two variables that we can achieve the same result. We can either increase voltage for the same wire feed, which increasing voltage will wet this out flatter, or we can keep the voltage where it is and we can just lower our wire feed. And by lowering our wire feed, that will also cause it to flatten the weld out, but lowering wire feed will cause the weld, the size of the weld, to change. Okay, so we need to make a determination, is this weld appropriate in size and width for this thickness of material? I would say that it is. If it was, a third thinner than this based on my travel speed, like, let's just say a real thin weld, I would say that we would need a wider, bigger weld, therefore we would need to increase wire feed to get a bigger weld. But I think based on what I'm seeing here, the weld size is appropriate. So to get a flatter weld, I'm going to run a little bit more voltage. Now I'm going to cool this down so that the preheat of this plate has no effect on our next pass. So again, settings don't matter at this point. We're learning heat to metal ratio. So all I'm going to do is I'm going to bump up my voltage 1 volt. Where it's at, again, does not matter. Now right away, we can see a drastic difference in how orange, you can still see it's glowing in there. A 1 volt increase wetted the weld out, but it put a lot more heat into it. Everything stayed glowing a lot longer. Let me cool this off and then we'll look at it. So right away, we can see our heat affected zone lines, they're significantly wider. I mean, if my finger's a gauge, you can see how much wider our heat affected zone is. So that means we've had more heat to the amount of metal we deposited. From a weld perspective, there's no question it's wider. Now the end blew off because the heat was high enough that I should have moved faster and then cut it out while I waited there a little too long, chewed the plate right away. We can start seeing some evidence of melt through. I can actually feel a ridge there. The beginning start melted through. So all of these, and actually you can see how much drastically different. There's my finger on the heat affected zone and it completely covers there. You can still see the edges. Much more heat. So our heat to metal ratio on this, more towards heat. So that's running hotter. This is more appropriate for what we're looking for. So now I'm going to run colder. I'm going to drop 2 volts from this, so 1 volt lower than this, and we're going to run a weld and look at it. So this weld, I ran about 1 volt under here. I slowed down quite a bit at the end, which caused it to wet out a little bit and get wider. But the voltage, you can see how it's starting to crown up quite a bit. And to do a little better of a job, I'm going to drop the voltage a little bit lower than what it's at. That was more what I was looking for. You can see how narrow that weld became, how humped up it is. It's literally like a bead of caulk on plate when you compare that to our more ideal weld. Very, very narrow. When we look at the back, very minimal evidence of penetration. And if you look at the heat affected lines, and you can actually see it right here, very close to the weld. See how much further that is? Our heat to metal ratio here was very low, which directly resulted in a more humped up weld. Now, on thin sheet metal, this would be more appropriate where you don't want to blow a hole. However, on anything over like thin sheet metal, you're going to find that although I made a bead on plate here, had I actually tried to do like a fillet weld, you're not going to have any penetration, and it's going to be very difficult to get them to wet together. You're going to have all sorts of indications of poor welds, like cold toes and stuff. But anyways, you can see ideal, too hot, little bit too cold. You can compensate quite a bit for a lack of heat just by slowing your travel speed, but beyond a certain point, like you're just going to start getting more roped up, etc. Now keep in mind, this is only 3.2 millimeter 1/8 inch plate. If I were to use these same settings on quarter, so over 6 mil plate, all of these are going to be way too cold. And I'll show you that now. I'm going to use the same settings as this, and I'm going to make a weld on this plate, and I'll show you. So you look at the results of that, even compared to our 1/8 inch plate, and what do we have? Extremely narrow heat affected zone, a literal bead of caulk on plate. I mean, just look at that. So what's wrong here? Well, our heat to metal ratio is off. So heat to metal isn't just about the metal referring to the wire that you're running or the electrode, but also the thickness of the material. Now, what we need to ask ourselves is, well, what's wrong here? Is something wrong here? Well, the answer is yes. Our bead is humped up like caulk, so means no penetration. That's unacceptable. So yes, we have something wrong here. The next question we need to ask ourselves is, how can we fix this? Well, with stick welding, if you see this, number one thing is it consistent in width and height? The answer is yes. Then to fix this with stick, increase amperage, try again. With wire feed, we have two variables. So the question we need to ask ourselves is, do we need more heat, more wire, or both? So to figure that out, we need to ask ourselves, is this weld appropriate in size for this thickness of material? I would say no. This is a very small weld, so not a lot of weld material for this thickness of plate. So right off the bat, we need to increase wire feed beyond where we're at. But if we add more wire, we need to increase heat to compensate for that. But to prove a point, what I'm going to do now, I'm going to keep our voltage the same right where it's at. I'm just going to increase wire feed so we can see what happens when we go too far out of the ratio, so far too much wire. So what do we have here? We have an even taller, not any hotter weld. See that? I mean, literally, we made what we had worse. Now the question is the weld metal amount that we deposited here adequate for 1/4 inch plate? Well, if you look at the quantity of metal there, that might actually make a decent weld on 1/4 inch plate. However, not run as cold as that. So at this point, we need to say, all right, rather than trying to adjust a ton of variables at once, let's just increase the heat input and see if we can't get this amount of metal to flatten out and produce a better looking weld. So that's what I'm going to do now. I'm going to increase the voltage 2 volts over what it is. We're going to run a weld and we're going to see what happens. So right off the bat, look how much that flowed out, it widened out compared to this. Look at that, a 2-volt increase in voltage. We went from that literal bead of caulk to something resembling an actual weld where the toes are somewhat flowed out, looks significantly better. We're on to something here. Now, based on my experience and knowledge about flux core wire welding, I think that we still need some more voltage over what we're seeing here. I just don't like the way that it's still a little bit humped up. And if we were actually welding 2 plates together like in a fillet weld, this would be too cold of a setting, because you have to remember, guys, running a bead on plate is going to take less heat than virtually any other joint you might weld. So once you get to run decent looking welds on plate, that's great. Factor in that you're going to have to run 5–10% more values than where you're at on actual joints, because you have far more metal to melt through. Because again, heat to metal ratio. If we just have this, we only have our wire in this plate. If we add an additional plate, we now have more metal, therefore we need more heat. The amount of metal you increase, be it the amount of wire you push or the amount of metal you're trying to fuse, all tips the ratio more towards metal than heat, therefore more heat to balance everything. It's just an equilibrium of sorts that you need to maintain. So based on this, I'm going to increase the voltage another volt, and we're going to take a look at it. So let's take a look at what we have. We have a little bit of porosity there on the start, which don't pay any attention to that realistically. But we can see increase in voltage, increase in heat input. Our weld is now wider than our previous one. You can see that, wider. And keep in mind, the travel speed between these two are very similar. So the fact that this is wider is not an effect of putting more metal down. It has to do with the voltage increasing. Our penetration likely has slightly increased as well. The other interesting thing is, you see how you can see ripples slightly in this? And in here it more or less is smoother. The higher your voltage or the higher the heat input is, the more liquid this puddle is going to stay, and a liquid puddle will self-level and essentially remove all of this ripples. And you can see, I'll bring it up, how much smoother that is. Same thing, you can see ripples here from my movement. The same thing applies to MIG. With MIG, in order to get a stack of dimes, you really have to typically run colder settings to get that appearance, which colder settings means less penetration, which is not necessarily a good thing with welds. Now, based on, you can see, roped up, flatter, flatter. The question is, where do we go from here? Well, that porosity, which I said don't worry about, could be an indication that we're running a little bit higher on voltage for the amount of wire we're feeding, and it could be due to any number of reasons. But I said not to worry about that, but it is something to take in consideration. What I would say is this weld here adequate in size for 1/4-inch material? I would say that it's a little bit on the small side for 1/4-inch. This would be a perfect weld size for 3/16. So I think what we need to do is bump up the wire feed a little bit to deposit a slightly bigger weld. So what I'm going to do is keep the voltage the same as where we're at here, and I'm going to run a pass here with slightly higher wire feed to deposit a bigger weld. So let's take a look at this. Without question, we have deposited a wider, bigger weld than previous, because now our wire feed is higher than any setting here. Now this was our most recent one. You can see the bead appearance between these two is pretty similar. It's just that this weld is a little bit bigger. We don't have any evidence of porosity, which is good. This is a pretty happy equilibrium for weld size. On 1/4 inch, it's still a little bit on the small side for like a fillet weld. So what I'm gonna do is I'm gonna increase the wire feed again to even higher settings than this. Same voltage as this, and we're gonna watch as the weld is produced and it's gonna start roping up more like these guys. So take a look at that. It's created a peaked bead shape. Now I didn't clean the toes very well. The toes are wetted out decent, but it's a narrower weld. Again, you can see it there. Very like a triangle shape versus a little bit better here. So based on what we see there, you got to ask yourself, is it cold or is it hot? Well, it's more peaked. It does not seem to be wetted out decent. I mean, it's decent, but it could be better. Had I ran that on a fillet weld, we would see all the indications where the bead would look more like this because there just isn't enough heat. So let's take this setting and I'm going to increase the voltage by a volt and a half. We'll do a 1.5 volts and we'll see what happens, and I'll run another one. So I went up a 1.5 volts on that right here compared to this weld, which you can see kind of crowned up. Look how it flattened it out a little bit. Not a lot, a little bit, looking pretty good. So I think we can put a little bit more heat to metal on this, and I'm gonna run another pass right here. I'm gonna run another 3/4 of a volt higher. So I bumped up the voltage even higher. You can see it flattened it out even more. And when we look at that, same wire feed, flatter. And now we're starting to see evidence of porosity, not just at the end, but along the toe line. And that's, our voltage is starting to get a little bit too high for our given wire speed. Now we're also, you see how there's no ripples in that, despite I was oscillating like this? And it even looks, oops, sorry, looks like there's some possible pinned up porosity there. Anyways, there's no ripples, and that's because it was run hot enough that the heat to metal ratio favored the heat end of things far more than the metal. Now with flux core, ideally, you want to see some ripple. So more or less like this here, between this and this. I mean, if it's perfectly flat with gas shielded flux core, or excuse me, self-shielded flux core, that's also acceptable like this. But you want to watch out, because if you start getting pin dot porosity like that, your values may be a little bit too high. And you know, if you run gasless flux core like with a straight drag angle and no manipulation, you're going to get a smoother bead than if you run it with a slight stitch movement. But yeah, looking at that, I would say that that's a little bit too much voltage. So just a pinch lower, and that would be very acceptable for what we're doing for these beads on plate, and that's what you should be aiming at. And again, you can see how much of a drastic change a couple settings are. So now what I'm going to do is I'm going to weld up a test plate of sorts, and then we're going to go through it together, and I'm going to test your knowledge so that you guys can develop the skills necessary to troubleshoot your own welds. So let's get into that. All right, so I got a plate here, this is the one that we welded together. I cleaned it up. We're going to go through it as kind of a test run, and then we're going to go through this other one I welded and kind of do some testing of sorts on you guys. So let's start out on this left weld here. Based on what you can see here, what can we figure out? Well, the width of it seems maybe a little bit wide. It's a little bit roped up, not too much realistically. Seems for this 1/4 inch, a little bit over 6 mil plate, seems to be pretty acceptable. I would say this is a reasonable pass. The stop I could have filled in a little bit better. Now this next one, honestly, I like the results of that a little bit better. It's more consistent, start to finish. Not too bad either way, both of those are good. Now this guy, clearly, caulk on plate, unacceptable. You do not want to have that. If you see this, what do we need to do? Well, question number one, is the amount of metal there that's deposited a decent amount for the thickness of material we're welding? I would say no. So we need a bigger weld, thus we need more wire feed. In the case of stick, we would need to step up to a bigger rod more than likely, but we need more heat. So in the case of this, if you deposit a weld like that, step number one, increase heat, be it higher voltage or more amperage. Then with more heat, base your determination on stepping rod size up or your wire feed speed up based on whether or not when it's wetted out, if the weld is acceptable to you or not on the width. This guy, what do we got going on? Appears to be a little bit less crowned up, but still unacceptable. Again, same deal. We need to increase the voltage to get it to wet out better. Based on that, we can make a determination if we need to run a larger rod with stick or more wire feed with your wire processes. Now this weld, how is that looking? I would say really good overall. It's wetted out. Could be cleaned up a little bit more. This is pretty acceptable for a bead on plate for practice. That's looking pretty good. These clearly are a little bit hotter, but you know, this I would say is fine for a bead on plate. This may be too cold to do a fillet weld. These may come out better on a fillet weld, because remember, the more metal that you're trying to weld together, the more heat it takes. So even though these two welds are clearly hotter than this, when you're welding two pieces together, it may actually still be too cold and your weld may end up looking like this more than it does this. So this, very acceptable, looking good. What about this guy? Seems to be, I would say, a little bit roped up. Not really, I guess, but it is flatter than this. So based on that, I would say the bead profile is looking pretty good. The porosity at the start, I wouldn't worry too much about. That's kind of the nature, and you have to remember I didn't clean any of this mill scale out. Flux core is going to have that. I wouldn't worry too much about that. And then let's look at these two beads again. Higher heat input than this, and also more wire feed. If you look at how much bigger that weld is than that. Is this an acceptable weld, both of these for 1/4 inch? I would say yes, this being bigger than that. Overall, like for 1/4 inch, if your welds look like this, you're doing pretty good. If it's the 3 in the middle, 2 roped up, etc. But these you can fine tune to get exactly what you want. These you need a lot of work on to get those in line. Now, it goes without saying, on 1/4 inch like this, the window that you have of what's like good versus bad is a massive window, okay? When you're trying to weld on thinner stuff, like even this 3.2 mil, this 1/8, the window of what is good and bad becomes from this massive window with thicker plate to like a smaller window. And then when you go and try and weld sheet metal, your window of acceptable or blowing a hole or too cold is so minor that that's why it's so hard to weld thin material, is that what's good and what's bad, it could be a 1/2 volt and 10 inch per minute on wire feed. And not just that, it could be a 5% change in your travel speed. So, you know, the variables become, what works becomes very, very minor, very controlled the thinner you go. The thicker you go, like I could run it twice as hot as these and still deposit a weld without a doubt, because it's so thick it can take the heat. So now let's go on to a little bit of a test. We're going to do this simply because, well, I can't be there with you to go through this. So we're going to have to do this where we'll start out and I'm going to mention this weld. We'll talk about this one. So stare at this weld where my finger is and think to yourself, what do you see here? Based on what I see here, since I'm not doing a written test here, I'm going to give you my thoughts. Definitely cold, it's roped up. Is a weld the appropriate size for this 1/4 inch? I would say it's a little bit probably on the small side for the amount of metal, but what do we need to do to fix it? We need to increase our voltage. In the case of stick, if it looked like this, we would need to increase our amperage. 10–20% minimum, retest, see if it's better. All right, what do you see on this weld number 2? And what do you think you need to do to fix it if you feel that it needs fixing? Based on what I see, it looks more roped up than this. So again, our heat to metal ratio is far off. The solution to fixing this should be increasing voltage significantly. Now, based on what I'm seeing, the amount of metal here might actually be enough metal for 1/4 inch plate for a single pass weld, or at least a decent solid weld bead size. So I think we should leave the wire feed alone, increase the heat input 20 to 25%. So in the case of wire feed, up at 2 volts. In the case of stick, 15 amps, roughly. All right, let's move on to the next one. Don't put too much weight in the evidence of porosity. I forgot to mention that. So do you think it needs to be fixed? What can we do better? Again, this one right here. Based on what I see, number one thing, there's some inconsistencies. The start wide, middle, neck down, end wide. That's telling us that evidence that our travel speed is inconsistent. We want to be same width, the same, you know, all the way through the whole weld. So number one, we need to work on consistency. Number two, it definitely seems to be flatter than these, which is telling us that it's probably hotter. The weld amount of metal, the weld metal, seems to be decently appropriate. So based on what I'm seeing here, I think if anything, maybe drop the voltage 1–2% or drop the amperage, 5 amps, and just work on being more consistent. And I think that will drastically improve. Now this weld right here, what do you guys see? Based on what I see, I would say that it's acceptable in profile. The weld size is pretty decent. Seems to be run a little bit on the hot side, but it is just a bead on plate, so that's not too unexpected. If we're actually doing a weld joint, I think this would turn out pretty good. I would say that that's overall acceptable. If you see something like this, that's, for doing actual fillet welds, lap welds, that's pretty acceptable. If we could change anything, like I said, maybe slightly less, 1/2 volt or 5 amps might help to drop the amperage. This guy, what do we see? Again, don't place too much weight on any kind of porosity. Based on what I see, again, you know, if you eliminate the porosity, the actual weld, I would say, has more consistency than this guy. If the whole weld looked like this, where my thumb's covering the screw up, I would say very acceptable. Toes are not cold, it's wetted out very good, it has a good profile. So this is looking pretty good. By controlling the stop a little bit better would have solved that porosity issue. You can see the amount of underfill, like you cut out too fast, guess what? You know, your weld, if you look there, there's very little weld metal. So that's just simply working on stops. Now this guy, what do you see here? Again, don't pay too much to the porosity. Based on what I'm seeing, it seems to be excessively flat, which isn't necessarily a bad thing. The amount of reinforcement there, so the actual weld metal, seems to be actually less than this guy. This, if it didn't have porosity, would be acceptable. However, there may not be enough metal there that we deposited for 1/4 inch. So this would be possibly undersized. But again, you know, on 3/16 or, you know, a little thinner than this is like 5-6 millimeter, a little bit thinner than that, that profile would be acceptable. Again, don't pay any attention to porosity. Now, what about this guy? I would say, again, very acceptable profile to it. Much like these three, they're all, you know, in the ballpark of what you would want to be looking at for beads on plate. They're actually very similar. Now, I ran slightly different values, I will tell you this. So ran more heat, less wire, you know, more heat, etc. Just screwed around. And there's more than one way to skin a cat. Now again, the porosity that you're seeing has a lot to do with simply, well, for one, not cleaning the mill scale off at the start, which that's going to contribute towards the ending porosity. But, you know, when you start seeing it on this, yeah, we could drop the voltage a little bit. Same thing here. A little bit less voltage may have helped that, a little bit more wire feed, but not too bad. Now this guy, what do you see? Again, very, I would say, acceptable profile. It's a little bit flat when you look at it, but not bad, I would say. So again, the overview of this plate is that a lot of these welds, minus the evidence of porosity, are in the ballpark of what you should be looking at for size. If I had to pick one that I would say is the best out of these, based on what I see, for flux core, this guy right here and this guy, if it was a little bit more consistent, and this, you know, these right here, these here, and maybe a little bit of that one, is about what you're looking for 1/4 inch plate. You know, not humped up like this and not overly flat. You know, I mean, even so, this one's a little bit overly flat, but you get the idea. I mean, this here for profiles are looking pretty good. These here, not so good. And again, you know, the differences between those are far less than these. It's just to give you a little bit harder of a challenge to get you to think more about what's going on. So let's go to the conclusion. So in conclusion, what did we learn today? Well, we learned that your heat to metal ratio is very important. And if it's out of line too far, you're going to lose penetration, or you're going to run excessively hot and get undercut, etc. Now, one of the things I did after I cut the camera off is I ran a bunch more test welds and adjusted settings on my welder to try and eliminate some of the starting and ending porosity that I was seeing. And like I said in the video, not to put much weight in that, and by just changing a few settings on my welder, I was able to pretty much eliminate it. So I started out with this guy here. You can see starting porosity, ending porosity. This one here pretty much got rid of the starting porosity. Ending porosity is still there. So then I switched over changed some more settings, little bit of starting porosity, but looking a lot better, and then no ending porosity. And then this guy has virtually nothing on the start, and then the end is clean. And what I adjusted, and maybe your welder for wire welding has this, maybe not, but by changing my burn back setting, I was able to eliminate the ending porosity. And the burn back was factory defaulted at, I think it was 0 or something. I changed it to a 5 out of 10. And look at that, there's no more ending porosity and it no longer blows out the end of the plate. So I think it was just set far too high or whatever. Not really sure, but little simple tweaks can make all the difference in the world. The other thing is I adjusted my welder's running speed, and that's how fast the wire comes out at the start of a weld. That can be very critical because too much or too little wire at the start can contribute towards porosity as well. So that really went a long way to cleaning this up, you know, removing that porosity. And that's the thing, is that it doesn't matter, you know, who you are or how much experience you have. Little tweaks go a long way to fixing issues you have. And that's kind of the point of this video, is to show how important making little changes to make things better really is. And the first step to that is you have to recognize and ask yourself questions when you look at your welds. Is, you know, is it cold? Is it hot? You know, cold here or hot here? What's going on? Is the weld the appropriate size? Just to sum up everything and cash this video out, pretty much if you're new to welding and even fairly experienced, you're going to have to make tweaks and figure out how to fix things. And this video hopefully will serve as a tool for your toolbox, aka your brain, to give you the correct tools to solve issues that you're going to face. And no matter what process, all this stuff applies to it. So, you know, TIG, MIG, stick, you can all benefit from understanding your heat to metal ratios. And with that said, thank you guys for sticking around for another video. I appreciate it. Appreciate all the comments you guys leave and the thoughts that you give. And this video wasn't a viewer recommendation, but with talking with a lot of you guys, I think that this will help you out. So with that said, thanks for sticking around. Till next time.